Welcome to Unit 6 of GIS for Disaster Risk Reduction. In this unit, we'll explain the concept of geospatially enhanced risk assessment. We hope you're convinced by now that GIS can play an important role in risk reduction. So we will now dive a bit deeper and explore the ways in which it can help and even use some of the tools to start putting this into action. While GIS has many ways to contribute to risk reduction, risk awareness is perhaps the most essential. Because without having a good understanding of the nature of risk, good decision making and prioritization is not possible. First, let's consider the simple formula for risk that we've been using. This is a unitless construct to help us understand how hazards and vulnerabilities interact. The key reason that we use a multiplication operator is that if either hazard or vulnerability is equal to zero, the risk we're concerned with does not exist and will also be numerically represented as zero. While this formula is sufficient for our needs, mitigation planners and risk reduction experts have more comprehensive formulas that consider additional variables such as frequency of events, intensity of the hazard, and assignment or assessment of the consequences that might be visited upon a community. These can add meaningful insights and can be added to a simple analysis as the information becomes available. Known risk, systematically defined, provides a baseline for mitigation activities and adaptive approaches to reduce vulnerability or hazards. GIS provides a unique platform for integrating this information to the only aspect these features are likely to share: location. Through thoughtful design of our GIS, we can allow these inputs to interact in meaningful ways to provide us new information useful to disaster risk awareness and prioritization. This platform can integrate data from multiple disciplines and various levels of sophistication, which means we can begin to develop this analysis with what we have and replace it with better information as it becomes available. When using GIS for risk assessment, one needs to make sure that we don't get wrapped up in the technology to the point where we think that our analytical approaches and data needs to be highly sophisticated and robust. As you approach this, consider the saying, don't let the perfect be the enemy of the good. Where none exists, a risk analysis written on a piece of paper is better than none at all. While the GIS system has great complexity, the analysis we perform does not need to be delayed by the quest for excellent, highly detailed, and validated data. This slide presents a continuum of approaches that can be employed progressively as an organization matures in its use of these tools. The approaches start with a simple binary model where the hazard polygon is overlaid on the vulnerability, and those assets contained in the hazard boundary are considered effective. Each progressively more sophisticated level of analysis adds more granularity and spatial disaggregation to the hazard based on intensity, while providing a complementary enhancement to the fragility of the asset inventory, from simple stratification such as low, medium, and high vulnerability to a more robust analysis that includes probabilities and even annualized costs to plan for emergency funding reserves. The key to developing this is a modular approach where less sophisticated data can be replaced with better sources, increasing the quality and utility of the analysis over time. In fact, recalling our stone soup discussion from Unit 3, the GIS is little more than a water-filled pot, and you bring the long-term vision and strategy. In some ways, the first iterations of such an analysis can be educational to show the art of the possible. Should you be provided adequate resources to elevate the analysis to a point where decisions can be confidently supported. While we describe this as a continuum, the need and purpose of the tools will drive the use. So there are examples of extremely sophisticated data being used in the more simple upper tiers of this list. For example, billions of dollars are spent within the United States to map out flood hazards. This provides a detailed flood zone delineation that decision makers are confident in. One of the primary uses of these tools is to determine if homeowners need to purchase flood insurance. In this case, it's a simple cookie cutter analysis. If their structure is in the flood area, then they need to buy it. If it's outside, then it's optional. The point here is that a mature use of GIS in risk reduction employs multiple approaches, from the simple to the sophisticated. Before we move on, let's make sure we have some of the key elements of a GIS value proposition in place, as this may be useful to your understanding and for advocating within your organization. Often risk analyses are carried out by consultants, and given the costs and other burdens associated with this mode, they're infrequently completed and poorly maintained. In areas where land use and settlement patterns are changing, this can limit the shelf life of these reports and diminish their utility. The GIS approach puts the tool in the hands of the local community to provide a current state of risk as needed and on demand. Another great strength of this approach is the ability to use the GIS to model future planned conditions, either of the built infrastructure, changing hazard dynamics, or mitigation efforts. This allows the GIS to become a crystal ball of sorts, showing what the future change might mean to the community's risk profile. Users can explore impacts from hypothetical storms or evaluate the impacts of a construction project before either becomes a reality. Building on this, and with additional detail in the asset inventory, cost-benefit analysis can be completed to provide real numbers that show the benefits, for example, of a mitigation project and help ascertain if it's the best use of resources. This can help reduce the undue influence of politics and better inform decisions and investments in community safety and resilience. It must be noted that with all these benefits, the GIS does not make decisions, but supports decisions with tools that can manage considerable data and make it understandable in the context of the decision. It cannot handle all of the variables that affect the real world decisions that leaders must make. There are a few common approaches to risk studies that will be described in this section. The first is event specific that focuses on assessing the potential impact of a predefined scenario. Typically, this approach requires a user to define a hazard type, location, and intensity, and assess the impacts on the community. This can be used for planning, exercises, and advocacy, raising awareness of the community's vulnerabilities to energize the community for action. A mitigative approach combines the event-specific approach with the contingency planning and/or cost-benefit analysis discussed earlier. This approach is iterative and allows the user to run the hazard many times, but adjust the vulnerability of the key assets in the community and see how this affects overall risk. A less commonly used approach is to adjust the hazard for future situations, such as sea level rise. The high end of complexity is the annualized loss approach, which quantifies impacts and return period of a hazard type to estimate the resources needed for reserves in an annual budget. This is used to establish or replenish what is sometimes called rainy day funds or financial reserves for repair or replacement of uninsured community assets. Let's walk through each of these in more detail. As depicted in this graphic, an event-specific one-off study is a linear process where the study area is identified, the hazard is determined, the impacts are modeled, and reports are generated. Let's have a look at an example from the real world. Let's look at an event-specific example. For this one, we'll look at the impacts that could be expected on a coastal community if a historical storm were to occur again. Using a historical storm is beneficial for two reasons. First, it provides realistic hazard parameters. Second, if the event is sufficiently recent, some members of the community may have firsthand experiences from the storm and its impacts, which can enhance their understanding and appreciation for the consequences. Conversely, a hypothetical storm may be easier for some members of the community to dismiss, especially if it's at the high levels of intensity and low levels of frequency. For this effort, we'll employ the Hazards US or HAZAS tool developed by the US Federal Emergency Management Agency, since it gives us nicely formatted output for demonstration purposes. While this tool is designed for the United States, this limitation is a result of the asset inventories, not the hazard models. So it is conceivable that those outside the United States footprints, though it would take some effort. Okay, Hurricane Gracie came ashore in South Carolina on September 29, 1959, and caused considerable damage and killed 10 people near where it made landfall. While the storm did not have impressive damage numbers, this coastal area at the time, and in fact, just a few years prior, the first resort was built in Hilton Head Island, which is now home to over 40,000 people and considerable investments in property and infrastructure. So the question arises, What if another Gracie hit now? This report provides us with a full quantification of the building stock in the community to identify worst case exposure numbers. In this case, there are over 55,000 buildings worth over 7.5 billion US dollars. From this report, we can also see the categories that HAZIS uses to study building inventories. This is likely a combination of discrete and aggregated data for the total number. Following the storm, the GIS compares the storm intensity modeled with the inventory and its fragility to identify what might be impacted and provide totals for analysis. From this graphic, we can see the damage categories employed by HAZIS, ranging from none or no damage to total destruction. These damage classifications are often a source of discussion, and they should ideally be defined to reflect operational realities in the field. For example, severe and destroyed may be uninhabitable, and you can estimate that these people will need other accommodations. Their differences may be in the cost of reconstruction. Perhaps minor and moderate are habitable, with minor having largely cosmetic damage, and moderate can be made habitable with some plywood or plastic sheeting. Look at the numbers. While they may seem high, looking at the percentages suggests that they must have built well in this area, understanding the risk these storms pose. One thing I recall about my time in Hilton Head is that they're rich with trees, which provide welcome shade but cannot be expected to resist hurricane force winds. HAZIS populates boilerplate paragraphs like those in this slide with numbers conveying modeled estimates. In this case, they expect there to be 3,438 truckloads of debris, 96% of which will be tree debris. They also expect there to be 332 people in need of temporary shelter. The result of an event-specific study like this provides a single set of numbers that can be used to raise awareness of risk and open people's eyes. But to really make a difference, we'll have to go a bit further. First off, you should notice one big difference with a mitigative study, a loop in the process. This loop can be run as many times as necessary to find the best return on investment for each disaster risk reduction dollar, gourd or colones. From the Gracie example, we'll look into the fragility parameters of the asset inventories and improve compliance with the building codes, move or elevate structures, and possibly identify structural mitigation efforts that could be employed. We would track the cost to the community and government for each of these and rerun the model to see how the impacts are reduced. By recording the estimate cost of the initiative, it can then be compared to the benefits of reduced loss, life, and property. While this is very informative and can be ideal for developing risk reduction plans and programs, it does not take into account the likelihood of a Gracie type event ever occurring and the level of the resources that might be needed. To better understand costs in an annual budget model employed by most governments, it's important to understand how much funding should be kept in reserve per year to cover the anticipated costs from such an event. The annualized loss will include a probability estimate for a range of storms to not only plan for the major events, but the more frequent smaller events as well. The annualized loss estimation suggests how much money should be put away to cover these costs. Although this sounds like a solid number for planning, investments in risk reduction should reduce this annualized cost. So this too could be an iterative model like the mitigative study, where future investments in mitigation are offset by reductions in the annual deposit in the rainy day fund. Okay, let's shift gears back to the technology. The information products listed in the slide demonstrate the range of outputs available, but let's dive a bit deeper into how these are arrived upon. We need to understand the outputs from these analyses if we're going to make good use of the effort. As we saw from the HAZIS example, the basic methods for high-level reporting is to use aggregated data to provide the big picture summaries. Also, these models can be quite good at estimating overall numbers, but can fall short when looking at discrete impacts on individual assets. The reason for this is similar to conducting surveys, where the law of averages smooths out the anomalies and accuracy of the total numbers and trend tend to improve with the number of data points. Discrete data can be analyzed similarly, but it's best to assess each asset in terms of probabilities of damage levels being experienced. Let's explore these different approaches. Looking at the graphic to the right, assume at, assume at first the example is for assessing likely impacts on housing stock. Let's say, for example, there's a 20% in the red or completely damaged, 50% in the orange, extreme damage, and 30% in the moderate category. For the aggregated data, we would translate this into the housing inventory and enumerate the results based on their percentages. If there are 1,000 structures in the study area, to keep the math simple, then 200 are estimated to be completely destroyed, 500 should be extensively damaged, and 300 moderately damaged. Now, if this curve was representing discrete data on hospitals, fire stations, and police stations, for example, it would associate the numbers with the probability of the structure being in one of these damage classes. So a structure represented by these curves would have a 20% chance of being destroyed, 50% of extensive damage, and 30% chance of moderate damage. For summary reports, the model might then be assigned to the majority class and added to it. So in a sense, all data is aggregated in the reporting, some spatially and others categorically. Out in the public domain, there are a small number of specialized software programs that are designed to facilitate these types of analytical efforts. Typically, they provide the means to quickly analyze hazards and risk data together for outputs with varying complexity and sophistication. Most provide reporting features to quickly convert the analysis to actionable information products. Although these tools are powerful, sometimes they might not fit the bill due to limitations in the community's data or difficulties localizing the data to the context of the community being studied. In these cases, you can create models in the GIS software to replicate this process, but fit the situation. You can also do this with paper maps, clear plastic overlays, dry erase markers, and other analog tools. The three best known tools in this suite of software applications are HAZUS, CAPRA, and InnoSafe. HAZUS is a long-running loss estimation program from FEMA that is based on the popular commercial GIS software ArcGIS from Esri. This application has hazard models that build hazard footprints from event parameters. It has inventory data for the entire United States that can be replaced with more accurate or current local data. It has sophisticated fragility curves and models to assess primary and secondary impacts. Finally, it has custom reporting tools to convert all of this processing power into products for broad consumption in the disaster mitigation and risk reduction discipline. It's used by disaster managers in iterative mitigative modeling applications to optimize mitigation investment from flood, earthquake, and tropical cyclone winds. CAPRA stands for the Central American Probabilistic Risk Assessment Program and was created with funding from the World Bank. The program seems to be dormant, but in its prime, it had a similar approach to HAZUS, but was more broadly applicable across the world, and additional modules for volcano, landslide, and other hazards were included. InnoSafe is a plugin for the QGIS open source application you were introduced to earlier, and you'll gain firsthand experience on this tool in this unit's exercise. GIS software applications allow for the building of models, which are really just recorded analytical steps in a progression to convert a series of inputs into desired outputs. So in cases where HAZUS or InnoSafe are not applicable, by having an understanding of how these analytical software work, we can still advance in our risk awareness efforts by building similar models in the GIS. In a sense, we can reverse engineer HAZUS or other tools to provide the outputs we need. Going even lower tech, the concepts of GIS analytics for DRR do not even require computers. Like John Snow's cholera exercise, GIS for disaster risk reduction does not have to be in a computer. It can be managed with transparent overlays on maps. It can be hand-drawn or even physical models demonstrating the concepts and exposures. This is often a preferred way when working with extreme rural or underdeveloped areas where the computers might be a distraction or difficult to leverage. Also, it might be a good low-cost first step to building momentum for such a project. Okay, enough talking about it. Let's get to doing some work and learning from doing. In this exercise, we'll go back to QGIS and use one of the many plugins available to tailor the software for specific use. The InnoSafe tool was developed to help provide a simple but reliable tool for assessing risks in Indonesia. From using physical models to sophisticated computer applications, there are many approaches that can be considered for use alone or in combination to start a GIS for disaster risk reduction effort, and careful consideration should be taken before selecting. Part of that decision-making process should include your plans for growth of the effort to keep pace with the needs of your community. It's better to start on the lower end of sophistication continuum and advance from a position of success rather than going for the top end and falling short. The real power of these tools is in preparedness and mitigation planning come from using them cyclically as described in the mitigative approach. This allows for the exploration of outcomes given a range of controlled inputs and helps balance alternatives and optimize investments. Finally, we studied the full range of tools in order to understand how they work, knowing we may be able to replicate the most important and useful aspects through desktop GIS or analog means. We also want to know how they work so that we might find ways to bring them to bear through data development and customization in the future. Thank you for completing Unit 6. In Unit 7, we'll explore ways to enhance communicating what we learned from these studies.